The information provided in this video is for educational and entertainment purposes only and does not constitute professional automotive, legal, or safety advice. The physics discussed are based on general mechanical principles and historical trends in automotive engineering. Driving involves inherent risks, and vehicle dynamics can vary significantly based on make, model, environmental conditions, and maintenance. You should never attempt to replicate any maneuvers described herein or intentionally test the stability limits of a vehicle outside of a controlled, professional environment. Always follow local traffic laws, wear your seatbelt, and consult your vehicle's owner manual or a certified mechanic for safety-related concerns. The creators of this content are not responsible for any injury, loss, or damage resulting from the use or misuse of the information presented. Viewers are encouraged to conduct their own due diligence and prioritize safety above all else. Imagine you are driving down a clear, open highway at 65 miles per hour. The sun is out, the road is dry, and you feel completely in control of the 2-ton machine beneath you. Then, in a fraction of a second, everything changes. Perhaps a deer jumps into the lane, or a distracted driver swerves into your path. You jerk the steering wheel to the left. The tires howl. You feel a sudden violent tilt. The horizon, which was just a straight line through your windshield, begins to rotate. Your side window is suddenly filled with asphalt, then sky, then asphalt again. The sound is a deafening cacophony of shattering glass and shrieking metal. In the time it takes you to blink, your world has literally turned upside down. Most people believe that car rollovers are freak accidents, unpredictable acts of God that happen to bad drivers or people in top-heavy monster trucks. But the reality is far more calculated and, frankly, more terrifying. According to historical trends and data from the National Highway Traffic Safety Administration, while rollovers only account for about 2 to 3% of all vehicle crashes in the United States, they are responsible for nearly 35% of all passenger vehicle fatalities. This means that if you are in a crash that involves a flip, your potential outcomes for serious injury or death skyrocket by over 10 times compared to a standard frontal or side impact collision. We are entering a deep dive masterclass into the violent, precise, and often misunderstood world of automotive physics. This isn't just a video about car crashes. It is an exploration of the invisible forces that govern your everyday commute. Today we are going to break down exactly why a car, designed by some of the most brilliant engineers on the planet, can be defeated by a simple curb or a patch of soft dirt. We are going to look at why certain vehicles are predisposed to this kind of catastrophe and how the laws of motion, laws that were written by Isaac Newton centuries before the first internal combustion engine ever roared to life, are working against you every time you take a sharp turn. This video solves the mystery of the point of no return. You will learn the exact mathematical threshold where gravity loses its grip and centrifugal force takes over. We will explore case studies of vehicle recalls that changed the industry forever, and analyze the specific engineering failures that can lead to a roof crush. By the time we are finished, you will understand the concept of the static stability factor, the terrifying reality of the tripping mechanism, and why your choice of tires might be the only thing keeping your roof from meeting the pavement. To truly understand what happens when a car flips, we have to start with the concept of the center of gravity. Every object in the universe has a balance point, a single coordinate where its entire weight is concentrated. In a low-slung sports car, that point is just inches off the ground. In a modern SUV or a pickup truck, that point is significantly higher. This height is the primary variable in the equation of disaster. When you steer a car, you are essentially asking the tires to push the bottom of the vehicle in one direction while the top of the vehicle wants to keep going straight due to inertia. This creates a moment or a rotational force. Think of it like a tall bookshelf versus a short footstool. If you push the footstool at the top, it slides across the floor. If you push the tall bookshelf at the top, it tips over. Your car is that bookshelf and the road is the floor. But it isn't just about how tall the car is. It is about the relationship between that height and the width of the tires, what engineers call the track width. This ratio determines your vehicle's resistance to rolling. We will be examining data that shows how even a 2-inch difference in ride height can be the difference between a controlled slide and a catastrophic rollover. We will also delve into the trip. Did you know that over 95% of rollovers are tripped? This occurs when the vehicle's lateral motion is suddenly interrupted by an external object. It could be a curb, a guardrail, or even the tires digging into soft soil on the shoulder of the road. We will deconstruct the step-by-step physics of the trip, explaining how kinetic energy is instantly converted into rotational energy with enough force to lift a 4,000-pound vehicle off the ground as if it were a toy. We will also address the evolution of safety technology. You may have heard of electronic stability control or ESC. We will analyze case studies that demonstrate how this single piece of technology has fundamentally shifted the historical trends of highway safety. We will look at how sensors measuring your rate and steering angle can intervene in milliseconds, applying individual brakes to pull a car back from the brink of a flip. However, even the most advanced computer cannot rewrite the laws of physics. There are scenarios where the lateral g-forces are simply too high for any system to compensate. We are going to quantify those forces, looking at exactly how many gs it takes to break the bond between rubber and road. Furthermore, we will take a deep dive into the structural integrity of the vehicle itself. What happens to the frame when the car is upside down? We will explore the roof crush standards and how automotive manufacturers have had to reinforce the A, B, and C pillars to support the entire weight of the car in a rollover. This is a masterclass in material science, looking at high-strength steel versus aluminum and how the geometry of a roll cage, even a hidden one in a consumer SUV, is designed to preserve the survival space of the cabin. We will also discuss the role of the seatbelt, which is your only defense against the most common cause of death in rollovers, ejection. We will examine the data on centrifugal ejection, where the spinning motion of the car literally flings unbelted passengers through the windows. This is the most comprehensive guide to vehicle rollovers ever produced for this platform. We are going to cover everything from the J-turn maneuver, used by test pilots, to the mathematical modeling of moment of inertia. Whether you are a car enthusiast, a physics student, or just someone who wants to understand how to stay safe on the road, this deep dive will provide you with the level of insight that usually requires a degree in mechanical engineering. We are peeling back the layers of the everyday driving experience to reveal the high-stakes physics that are always in play, just beneath the surface of the asphalt. We are going to start with the very first millisecond of a crash, the moment the driver loses traction, and we won't stop until we've explained every vibration, every force, and every consequence of the car going upside down. This is the science of survival. This is the physics of the flip. Let's begin. To understand the violent mechanics of a vehicle inversion, we must first master the fundamental concept of the center of gravity, often referred to as the CG. Imagine a typical American driver in 2026. Let us call him Jordan, cruising down a suburban highway in a modern electric SUV. Jordan feels secure because his vehicle is equipped with the latest structural reinforcements, but physics does not care about brand names or safety ratings once certain thresholds are crossed. The center of gravity is the specific point in Jordan's SUV, where the entire weight of the vehicle is mathematically concentrated. In a standard sedan, this point is relatively low, often near the height of the door sills. In Jordan's SUV, even with a heavy battery pack mounted in the floor, a design choice in 2026 that has improved historical trends regarding stability, the CG remains significantly higher than that of a performance car. This height is the first half of a critical equation known as the static stability factor, or SSF. To calculate the SSF of Jordan's vehicle, engineers take the track width, the distance between the center of the left tire and the center of the right tire, and divide it by twice the height of the center of gravity. The formula is SSF equals T/2h. This number is the most reliable predictor of a vehicle's likelihood to roll over in a steady-state turn. A low-slung sports car might have an SSF of 1.50 or higher, while a top-heavy commercial van or an older model SUV might hover around 1.00 to 1.10. The lower the number, the more prone the vehicle is to a rollover. In the early 2000s, many popular SUVs had alarmingly low SSF ratings, leading to a spike in rollover incidents that eventually forced the industry to widen track widths and lower engine placements. Now, imagine Jordan is forced to make an emergency lane change at 70 miles per hour. As he jerks the steering wheel to the left, a phenomenon called lateral acceleration takes over. While Jordan's steering input tells the tires to move left, the massive weight of the vehicle wants to keep moving straight. This is Newton's first law of motion and action. An object in motion stays in motion unless acted upon by an external force. The tires provide that external force through friction with the asphalt, but they only pull at the very bottom of the car. The rest of the car, specifically the mass concentrated at the center of gravity, continues forward, creating a rotational force or a torque around the vehicle's longitudinal axis. At this precise moment, a battle of vectors begins. Gravity is pulling Jordan's SUV straight down, trying to keep all four wheels planted. Simultaneously, the lateral force from the turn is pulling the center of gravity toward the outside of the curve. Think of it as an invisible tug of war. As the turn becomes sharper or the speed increases, the resultant force vector, the combination of gravity and lateral force, begins to tilt. As long as this resultant vector stays within the footprint of the tires, the car stays upright. However, the moment that vector moves outside the contact patch of the outer tires, the vehicle has reached its geometric tipping point. This is the point of no return. But a car is not a solid, rigid block of wood. It has a suspension system, and this is where the physics of a rollover becomes truly complex. As Jordan swerves, the springs on the right side of his SUV compress under the massive load transfer, while the springs on the left side extend. This causes the body of the car to lean, a movement known as body roll. This leaning motion is not just uncomfortable for Jordan, it is dangerous. As the body leans, the center of gravity actually shifts further toward the outside of the turn, further compromising the SSF. This creates a positive feedback loop. The more the car leans, the easier it becomes for the lateral forces to tip it further. Historical trends show that vehicles with soft, long-travel suspensions, such as those designed for off-roading, are particularly vulnerable to this effect during high-speed maneuvers on pavement. In a 2026 vehicle like Jordan's, Electronic Stability Control, or ESC, is working frantically to prevent this. The onboard computer is monitoring sensors that check the yaw rate, the steering angle, and the wheel speed hundreds of times per second. If the system detects that Jordan is entering a maneuver that could lead to a tip-up, it can autonomously apply the outside front brake to create a counter moment, effectively trying to steer the car back into a stable posture. However, even the most advanced ESC in 2026 cannot overcome the basic laws of friction. If Jordan's tires have too much grip, a concept known as side force, they will refuse to slide. In most accidents, sliding is actually a safety mechanism. If a car slides sideways, it is dissipating energy without flipping. The danger arises when the sliding stops abruptly. This leads us to a critical distinction in automotive safety: the difference between an untripped rollover and a tripped rollover. An untripped rollover is rare. It happens on flat, high-friction pavement when the lateral force alone is enough to overcome gravity. You see this in professional racing or with extremely top-heavy vehicles. But the vast majority of rollovers on American highways involve a trip. Imagine Jordan's SUV doesn't just lean. It begins to slide sideways across the asphalt. As long as he is sliding, he is in a high-risk situation, but the car is still right side up. Potential outcomes change instantly if his tires leave the smooth pavement and hit a patch of soft grass, a curb, or a guardrail. The moment Jordan's tires strike a curb while sliding sideways, the lateral kinetic energy of the entire 2-ton vehicle is instantly concentrated at the base of the wheels. The curb acts as a pivot point, much like a person being tripped by a wire at their ankles. The bottom of the car stops moving, but the top of the car, carrying all that momentum, continues. This is where the physics transitions from simple lateral acceleration into a violent angular momentum. The car is no longer a vehicle. It has become a projectile rotating around an axis. We can actually quantify this using the moment of inertia, which describes how difficult it is to change the rotational motion of an object. Because a car's mass is distributed far from its center, with heavy engines at one end and fuel tanks or batteries at the other, once it starts rotating, it is incredibly difficult to stop. Historical trends in crash data suggest that once a vehicle begins this rotation, the occupant's fate is largely determined by the first 90 degrees of the flip. This is the phase where the kinetic energy is at its peak. As Jordan's SUV leaves the ground, the tires are no longer providing any control. He is now a passenger in a tumbling mass of metal. In this 2026 deep dive, we have to look at the energy involved. A vehicle traveling at 60 miles per hour possesses enough kinetic energy to launch itself several stories into the air, if that energy is redirected vertically. During a rollover, that energy is dissipated through the crushing of the roof, the shattering of glass, and the friction of the metal scraping against the road. If Jordan is not wearing his seatbelt, the physics becomes even more grim. As the car rotates, Jordan is subjected to centrifugal force that pulls him away from the center of the rotation, meaning toward the windows. This is why ejections are so common in rollovers. If a window shatters and a passenger is not restrained, the rotation of the car can literally centrifugalize them out of the vehicle. But even if Jordan is buckled in, he faces the terrifying reality of roof crush and cabin intrusion. What happens to the human body when it is suspended upside down, held only by a 2-inch wide strip of polyester, while the roof above is being compressed by thousands of pounds of force? How does a 2026 vehicle's frame hold up when it is forced to support 5 times its own weight in a dynamic drop? And most importantly, what is the soil trip phenomenon that causes perfectly safe-looking SUVs to flip on flat dirt? We have only just scratched the surface of the physical forces at play. The moment the tires leave the ground, a new set of rules takes over, rules that govern the speed of the roll, the impact zones, and the survival space. In the next part, we are going to deconstruct the tripping point in granular detail and look at the one specific type of terrain that accounts for more flips than any other. To understand why a vehicle suddenly departs from its horizontal plane, we must look at the most common catalyst for a flip, the soil trip. While many people believe that most rollovers happen because of high speeds on sharp curves, historical trends show that nearly 70% of all fatal rollovers occur when a vehicle leaves the roadway. This is where the physics of the soil trip takes center stage. Imagine a driver named Sarah in 2026, operating a popular mid-sized crossover. Sarah is driving on a 2-lane rural highway when a momentary distraction causes her right side tires to drift off the paved shoulder and into the soft, uncompacted earth at the edge of the road. In this scenario, the transition from asphalt to soil is not just a change in texture. It is a fundamental shift in the mechanical interaction between the vehicle and the ground. On the paved surface, the coefficient of friction, often denoted by the Greek letter mu, is relatively predictable, typically ranging between 0.7 and 0.9 for dry asphalt. This friction allows the tires to grip the road for steering and braking. However, once Sarah's tires hit the soft soil while the vehicle is traveling at a high lateral velocity, the friction model changes from sliding friction to mechanical interlocking. The tires and eventually the metal rims begin to act like shovels rather than rollers. This is the gouge effect. As the vehicle slides sideways on the soft surface, the tires sink. The lateral force of the car's momentum pushes the side of the tire into the dirt, building up a mound of earth in front of the wheel. At some point, the resistance from this accumulated soil becomes greater than the force required to tip the car over. In physics terms, the soil creates a new pivot point or fulcrum at the very bottom of the tire. This effectively turns the entire height of the vehicle into a massive lever. The distance from the center of gravity to this new pivot point on the ground is what engineers call the moment arm. The longer this arm, and the more mass Sarah has in her vehicle, the more torque is generated to rotate the car around its longitudinal axis. To quantify this, we look at the lateral impulse. As the soil resists the side-sliding motion, it exerts an upward and inward force. Historical trends in accident reconstruction data show that once the lateral deceleration reaches a certain threshold, often exceeding 1 g, the vertical force on the inboard tires, the ones furthest from the soil, drops to 0. This is the exact moment of liftoff. In Sarah's case, the left side tires of her crossover lose contact with the pavement. Once those wheels are in the air, gravity is the only thing fighting the rotation, and in a high-speed trip, gravity usually loses the first round. What makes the soil trip so deceptive is that it can happen at surprisingly low speeds. While high-speed highway flips are more dramatic, potential outcomes for a rollover exist even at speeds as low as 25 miles per hour if the trip is abrupt enough. If Sarah's car hits a deep drainage ditch or a particularly steep embankment, the change in the angle of the ground itself accelerates the roll. This is because the ground is essentially rising up to meet the falling side of the car, shortening the time it takes to reach the tipping point. We must also consider the role of the rim. In a violent side slide on soil, the lateral pressure often exceeds the tire's bead seat strength. This causes the tire to debead, meaning the rubber separates from the metal rim. When this happens, the sharp edge of the alloy or steel rim bites directly into the earth. This metal-on-soil interaction provides a much more rigid and uncompromising trip than rubber ever could. This is why many rollover case studies show deep furrows in the earth where the rim acted as an anchor, flipping a 4,000-pound machine as if it were a gymnastic vault. Now, imagine the perspective from inside the cabin during these first 500 milliseconds. As Sarah's car begins to rotate, the sensory experience is one of total disorientation. In 2026, vehicles are quieter and more insulated than ever. But the sound of the rim digging into the soil is a visceral mechanical grind that vibrates through the entire frame. Because the center of gravity is higher in her crossover than in a sedan, the rotation accelerates quickly. This is due to the conservation of angular momentum. As the vehicle tips, the distribution of its mass relative to the pivot point changes, and the gravitational force actually starts to help the rotation once the center of gravity passes the vertical line of the tires. Another factor to consider in the deep dive of the trip is the load transfer. Before the car even leaves the ground, all the weight has shifted to the 2 tires on the side of the trip. In Sarah's crossover, this might mean that 2 tires are now supporting nearly 4,000 pounds of dynamic force. The suspension on that side is completely bottomed out, hitting the rubber bump stops. This turns the once compliant suspension into a rigid part of the lever. There is no more energy being absorbed by the springs. Every bit of kinetic energy is now being funneled into the rotation of the chassis. Historical trends also highlight the danger of the corrective swerve. Often, a driver like Sarah will feel the tires hit the dirt and instinctively jerk the steering wheel in the opposite direction to get back onto the pavement. This is known as a power-off or power-on overcorrection. This maneuver creates a violent weight transfer. The car is already leaning toward the dirt, and the sudden steering input in the opposite direction creates a massive pendulum effect. The car snaps back, the suspension loads and unloads like a catapult, and the vehicle literally launches itself into a roll on the other side of the lane. This is called a friction-induced or untripped rollover that was initiated by a tripping-like event. By deconstructing the soil trip, we see that it is a perfect storm of material science, soil mechanics, and Newtonian physics. The Earth itself becomes a tool that redirects horizontal speed into vertical rotation. But what happens once the car is fully airborne? What happens when the first corner of the roof makes contact with the ground at 60 miles per hour? The transition from the trip to the first impact is where the real destruction begins. In the next part, we are going to analyze the terrifying physics of the first impact, the mechanics of roof crush, and how the concept of energy dissipation determines whether a vehicle remains a protective shell or becomes a crushing weight. We will also look at why the first hit is rarely the most dangerous one in a multi-revolution flip. The moment of transition from the air back to the earth is arguably the most violent event in any automotive accident. Imagine David, a driver in 2026, behind the wheel of a heavy electric pickup truck on a rural road in Pennsylvania. His vehicle has already undergone a soil trip, and the 2.5-ton machine is now rotating through the air. For a brief heartbeat, there is a terrifying silence as the tires lose contact with the ground and the engine's roar is replaced by the whistling of wind. But physics is merely gathering its strength for the first impact. When the corner of the roof finally strikes the pavement or the hard-packed dirt, the kinetic energy that was previously propelling the truck forward and rotating it sideways must go somewhere. The first impact usually occurs at the roof rail, the reinforced metal beam that runs above the doors. This is the structural backbone of the vehicle's upper half. According to historical trends and federal safety data, the primary goal of automotive engineering in this millisecond is the preservation of the survival space. This is the volume of air inside the cabin that must remain uncrushed to prevent the roof from making contact with the occupants' heads and necks. To understand the forces at play, we look at the kinetic energy equation, KE equals 1/2mv. 2. Because David's truck is a modern 2026 electric model, it is significantly heavier than the internal combustion trucks of a decade ago, often weighing over 6,000 pounds due to the massive battery pack. When that mass is combined with a velocity of 60 miles per hour, the energy involved is staggering. At the point of contact, the vehicle is subjected to a dynamic load that can far exceed its own static weight. In the United States, the Federal Motor Vehicle Safety Standard 216, commonly known as the roof crush standard, dictates that a vehicle's roof must be able to withstand a force equal to multiple times its own weight. For many years, this requirement was only 1.5 times the vehicle's weight, but as safety research evolved, that standard was pushed higher. In 2026, high-performance safety ratings often require a strength-to-weight ratio of 4.0 or higher. This means David's roof pillars must be capable of supporting over 24,000 pounds of force without collapsing more than 5 inches into the cabin. But how do engineers achieve this? This is where material science becomes a life-saving tool. In David's truck, the A-pillars, the supports on either side of the windshield, and the B-pillars, the supports between the front and rear doors, are not made of ordinary mild steel. They are constructed using ultra-high-strength boron steel. This material is so hard that it cannot be cut by standard emergency rescue shears. It often requires specialized hydraulic tools. When the roof hits the ground, this boron steel is designed to resist deformation. It doesn't crumple like the front end of a car does in a head-on collision. In a frontal crash, you want the car to crush to absorb energy. In a rollover, you want the cabin to remain a rigid, impenetrable cage. However, even with boron steel, the physics of energy dissipation is a brutal reality. If the roof does not deform, the energy must be transferred elsewhere. Much of it is sent down through the pillars into the frame and the floor pan. This is why you often see doors jammed shut, or the entire body of a rolled vehicle slightly twisted. The energy is literally searching for the path of least resistance. If the impact is angled, it creates a diving motion. This occurs when the front corner of the roof strikes the ground, causing the vehicle to pivot forward. This adds a second axis of rotation, turning a simple roll into a complex, multi-axial tumble. Case studies in accident reconstruction show that the first impact is also the moment when the glass strategy of the vehicle is tested. In David's 2026 truck, the windshield is made of laminated glass, 2 layers of glass with a plastic interlayer. When it strikes the ground, it cracks but remains in one piece, providing a small amount of additional structural support to the roof. The side windows, however, are typically made of tempered glass designed to shatter into tiny, relatively harmless pebbles. The moment these side windows vanish, the structural integrity of the roof system decreases slightly, and the cabin is suddenly open to the outside environment. This increases the risk of debris entering the vehicle or, in the case of unbelted passengers, the risk of partial ejection. Potential outcomes in this first impact are also heavily influenced by the ground surface. If David's truck hits flat, unyielding asphalt, the impact is sharp and brief, sending a massive shockwave through the frame. If it hits soft soil, the roof may actually dig in, much like the tires did during the trip phase. This digging in effect can cause the vehicle to stop its rotation abruptly, or conversely, it can cause the vehicle to vault even higher into the air. This is the pole vault effect, where the roof acts as a lever, launching the rear of the car upward and increasing the total number of revolutions. Inside the cabin, the physics for David is just as intense. As the roof strikes the ground, the floor of the truck is still moving. This creates a vertical acceleration that can be several times the force of gravity. If David is wearing his seatbelt, he is held firmly in his seat, but his head and neck are still subject to neck loading. This happens when the roof deforms slightly and the occupant's head makes contact with the interior headliner. Even a small amount of roof crush can result in significant downward force on the spinal column. This is why 2026 safety systems include roll-sensing side curtain airbags. These are not like standard airbags that deflate instantly. They are designed to stay inflated for several seconds, providing a cushion between the occupants' heads and the hard interior surfaces and pillars during the entire duration of the roll. The data suggests that the first impact accounts for a significant portion of the total energy dissipation. However, it is rarely the end of the story. Because of the conservation of angular momentum, a vehicle that has begun to roll will likely continue to do so until its energy is exhausted through subsequent impacts or friction. Each revolution is a new calculation of force and a new test of the vehicle's structural cage. David is currently in the middle of the first revolution, but the physics of the second and third hits are often different because the vehicle is no longer a pristine machine. It is now a compromised structure with shattered glass and bent pillars. What happens when the car keeps spinning? How does the weight of the engine or the battery pack affect the speed of the subsequent rolls? And why do some vehicles seem to bounce down the highway while others slide to a halt on their roofs? We have analyzed the structure and the first hit, but the real complexity lies in the multi-revolution dynamics. In the next part, we will explore the terrifying physics of the second impact, the role of centrifugal force on the vehicle's fluids, and the specific reasons why a car rarely stops after just one flip. We will also look at the centrifugal ejection phenomenon in deeper detail, explaining why the windows are the most dangerous part of a rolling car. The first impact was just the introduction to the chaos. Now we enter the complex and terrifying realm of multi-revolution dynamics. Imagine a driver named Marcus in 2026, behind the wheel of a high-performance electric sedan. He has already completed the first 360-degree rotation. At this stage, the vehicle's angular momentum, represented by the formula L equals I omega, is the dominant force governing every millisecond. The variable I represents the moment of inertia, a measure of how the mass of Marcus's car is distributed, and omega is the angular velocity, or the speed at which the car is spinning. Because modern 2026 vehicles often place heavy components like electric motors and large battery packs low in the chassis, they act like a massive, heavy flywheel. Once that flywheel starts spinning, the conservation of angular momentum dictates that it does not want to stop. In a multi-roll event, each subsequent impact with the ground is a violent battle between friction and momentum. If the ground is a flat, paved highway, the car might engage in what engineers call a sliding roll. In Marcus's case, if his car strikes the asphalt again at an oblique angle, the friction between the mangled metal roof and the road creates a powerful braking force on only one side of the vehicle. This uneven friction can actually cause the car to yaw, spinning like a top around its vertical axis, while it is simultaneously rolling over its longitudinal axis. Historical trends show that these multi-axial rolls are far more unpredictable and destructive than a simple single-axis barrel roll, because the energy is being redirected in multiple dimensions at once. Now let us look at what is happening to Marcus inside that spinning metal box. This is where we encounter the phenomenon of centrifugal force. While physicists describe centrifugal force as a fictitious force, the result of inertia in a rotating frame of reference, to Marcus it feels like an invisible giant is trying to rip him out of his seat. It is the force pulling him away from the center of the car's rotation. If the car is rolling at a rate of 2 full revolutions per second, the outward acceleration acting on Marcus's body can easily exceed 5 or 6 gs. For context, that is more force than a professional fighter pilot experiences during a high-speed banking maneuver. This is the exact moment when the centrifugal ejection risk reaches its absolute peak. In many older vehicles, the side windows were made of standard tempered glass. The moment the car's frame tweaked or flexed during the very first impact, that glass shattered into thousands of tiny pebbles. Now, as the second revolution begins, Marcus is sitting in a car with wide-open portals where the windows used to be. As the car continues to spin, that 6G force is pushing Marcus's torso and limbs directly toward those open holes. If he is not wearing his seatbelt, or if the seatbelt pretensioner fails to stay locked under the extreme vibrations of the crash, Marcus becomes a human projectile. Historical trends in the United States indicate that partial or full ejection is the leading cause of death in rollover accidents. When a person is ejected, they are not simply falling out of a car. They are being launched at the same tangential velocity the car was traveling. They often end up in the path of the tumbling vehicle, leading to potential outcomes where the car crushes the occupant it was meant to protect. In 2026, however, Marcus's vehicle likely features advanced ejection mitigation technology. We must look at Federal Motor Vehicle Safety Standard 226, which has pushed manufacturers to develop side curtain airbags that stay fully inflated for up to 6 seconds. This is much longer than a standard side impact airbag, which deflates in milliseconds. These curtains act as a safety net, specifically designed to keep Marcus's head and arms inside the cabin during the entire duration of a multi-roll sequence. But it is not just the occupants moving inside the vehicle. We must consider the fluid dynamics of a car going upside down. Even in 2026, electric vehicles have complex cooling systems filled with glycol-based fluids, and traditional internal combustion cars carry gallons of flammable gasoline and oil. When a car is inverted, the fuel system's venting and delivery mechanisms are completely reversed. In a standard upright position, gravity keeps the fuel at the bottom of the tank, away from the vent lines. Once the tank is upside down, the fuel can flood the charcoal canisters or attempt to leak through the filler neck. Modern 2026 safety valves, known as rollover valves, are designed to snap shut the moment they detect an inversion. However, the hydrostatic pressure generated by the weight of the fuel during a violent spin can sometimes overwhelm these mechanical seals, leading to fluid spray. Furthermore, let us consider the debris. Inside the cabin, everything that is not bolted down, a smartphone, a laptop, a half-full water bottle, or even the loose change in the center console, suddenly becomes high-velocity shrapnel. In a multi-roll event, these items are whipped around the cabin by the same centrifugal forces affecting Marcus. A 1-pound tablet, when subjected to a 10G impact during a roll, strikes with the effective force of 10 pounds. Case studies have shown that non-restrained cargo is a significant contributor to secondary injuries, such as concussions or lacerations, during the rolling phase. Marcus's laptop, which was once sitting peacefully on the passenger seat, is now a flying blade of plastic and glass, rotating at the same frequency as the chassis. The second and third revolutions are also where the roof crush we discussed earlier becomes cumulative. Each time the roof structure hits the ground, the structural integrity of the A, B, and C pillars is degraded. Steel possesses a property called work hardening, but it also has a fatigue limit. If the first hit bent a pillar by 1 inch, the second hit might bend it 3 more inches because the original geometry of the support has been compromised and can no longer distribute the load as intended. The survival space, that pocket of air around Marcus's head, is shrinking with every flip. This is why the duration of the roll is so critical. A single 360-degree flip is often survivable in a modern 2026 vehicle, But a trip over that leads to 4, 5, or 6 revolutions tests the very limits of material science and structural engineering. As the car continues to tumble, the suspension system is also being torn apart. The lateral loads placed on the control arms, ball joints, and struts during a roll are forces they were never designed to handle. It is common for wheels to be literally ripped off the hubs during the second or third revolution as they dig into the earth. This changes the physics of the crash yet again. A car with 3 wheels and a jagged axle stub dragging on the ground will have a much higher coefficient of friction. This increases the deceleration rate, which might stop the roll sooner, but it subjects Marcus to even higher G-forces in those final jarring moments. We have to ask, how does the car eventually stop? Is it just a slow bleed off of energy, or is there a final definitive impact that brings the chaos to a halt? And what happens to the human brain during these multiple revolutions of high G spinning? The disorientation is more than just feeling dizzy. It is a total physiological shutdown. In the next part, we will dive into the biomechanics of the roll. We will look at vestibular disruption, the physics of centripetal brain strain, and the incredible tech in 2026 seats that tries to keep your spine from compressing when the world is spinning at 120 revolutions per minute. We are moving from the metal of the car to the biology of the driver. To truly understand the biology of a rollover, we have to look past the mangled metal and focus on the soft tissue trapped inside. Imagine Marcus again, suspended in his 2026 high-performance sedan as it completes its third revolution. At this moment, Marcus's body is a collection of masses, his head, his torso, his limbs, all being subjected to violent, fluctuating acceleration vectors. The first system to fail isn't his bones, it is his vestibular system. Deep inside Marcus's inner ear are the semicircular canals, filled with a fluid called endolymph. Under normal driving conditions, this fluid moves slightly to tell the brain where the body is in space. But when the car is spinning at 120 revolutions per minute, the endolymph is whipped into a frenzy. This creates a total sensory blackout. His brain is receiving signals that he is rotating on multiple axes simultaneously, while his eyes are seeing a strobe-like blur of sky and asphalt. This vestibular disruption is so intense that even if Marcus were able to reach for a handle or the door release, his motor coordination would be virtually non-existent. This disorientation is the precursor to a much more dangerous physical event, centripetal brain strain. We often think of a concussion as the brain hitting the inside of the skull like a ball in a box. But in a rollover, the physics are rotational. As the car tumbles, Marcus's head is being whipped in a circular arc. Because the brain is not a solid object, it has the consistency of soft gelatin. It does not rotate as a single unit. The outer layers of the brain, the cortex, begin to rotate faster than the deeper, denser structures like the brainstem. This creates a massive amount of shear force. In medical physics, this is known as diffuse axonal injury or DAI. Imagine a wet sponge being twisted. The fibers inside the sponge stretch and tear. This is exactly what happens to the axons, the long-distance cables of the brain, during a high-speed roll. Historical trends in trauma data suggest that these rotational injuries are often more debilitating than direct impacts because they affect the brain's ability to communicate with itself on a cellular level. As the car continues its trajectory, we must address the most common site of catastrophic failure in the human frame, the spinal column. During the fourth revolution, Marcus's vehicle strikes the ground roof first. In this millisecond, the roof deforms by approximately 4 inches. Marcus is held in his seat by a 3-point restraint system, but that system is designed primarily for forward impacts. In a rollover, the seatbelt actually allows for a small amount of vertical travel. As the car is forced downward by the impact, Marcus's body is propelled upward toward the descending roof. This is the pogo stick effect. When his head makes contact with the interior headliner, the kinetic energy of the entire lower half of his body, his torso, legs, and the heavy seat he is strapped into, is funneled directly through his neck. In physics terms, this is a vertical loading event. We can calculate the force using F equals ma, where the mass is Marcus's body weight and the acceleration is the sudden stop of his upward momentum against the roof. If the car strikes the ground with a vertical deceleration of 20 gs, a 180-pound man effectively weighs 3,600 pounds for a fraction of a second. This massive load is placed on the cervical vertebrae, specifically the C1 through C7. Potential outcomes of this loading include burst fractures, where the vertebrae literally explode under the pressure, or a diving injury, where the neck is forced into a hyperflex position, compromising the spinal cord. However, Marcus is in a 2026 vehicle, And this is where the engineering of the advanced bioadaptive seat comes into play. In the decade leading up to 2026, researchers focused heavily on what is called the survival space margin. Marcus's seat is equipped with pre-crash pyrotechnic tensioners that don't just lock the belt, they actually retract it by several inches the moment the rollover sensors detect an untripped liftoff. This pulls Marcus deeper into the seat foam, as far away from the roof as possible. Furthermore, the seat tracks themselves are designed with energy-absorbing crush zones. Just like the front of the car crumbles to save the engine, the seat mounting brackets are designed to deform vertically, absorbing several thousand newtons of force before that energy ever reaches Marcus's tailbone. We must also consider the internal organs. We often visualize the heart, lungs, and liver as being fixed in place, but they are actually suspended by ligaments and vascular structures within the thoracic and abdominal cavities. When Marcus's car is subjected to the high-G centrifugal forces of a multi-revolution roll, these organs shift. This is known as organ swing. As the car spins, his heart is pulled toward his ribs with several Gs of force. In high-velocity rollovers, this can lead to an aortic shear, where the heavy heart moves so violently that it tears the primary artery. This is a purely physical consequence of mass and momentum that occurs even if there is no direct impact on the chest wall. In Marcus's 2026 sedan, the side bolster airbags have been redesigned. Unlike the large, pillow-like bags used for side impacts, these are stiff structural tubes that deploy from the seat itself. They are designed to clamp Marcus's torso in place, preventing the lateral organ shift and keeping his spine aligned with the center of the seat. This is a critical piece of the physics puzzle. If the body stays centered, the forces are distributed across the largest possible surface area. If the body is allowed to flop around, a phenomenon called flailing, the forces become concentrated on smaller, weaker structures like the ribs or the collarbone. By the fifth revolution, Marcus's car is losing kinetic energy, but the physical toll is cumulative. Each time his head is whipped, each time his spine is compressed, and each time his internal organs are shifted, the margin for error narrows. The cabin is now filled with a fine dust from the deployed airbags and the smell of ozone from the electrical systems. But there is another factor we haven't touched on: the inverse pendulum effect of the heavy battery pack. In Marcus's electric vehicle, the weight is concentrated at the very bottom. While this makes it harder to start the roll, once the roll is established, that low-slung mass acts like a wrecking ball, dictated by the laws of circular motion. How does this massive weight affect the final moments of the crash? Why do electric vehicles often end up much further from the initial trip point than gasoline cars? And what happens when the car finally stops, but it stops upside down? The physics of the post-roll state are just as dangerous as the tumble itself. We have looked at the brain and the spine, but now we need to look at the vascular system under the pressure of being inverted and the terrifying reality of suspension trauma while trapped in a seatbelt. In the next part, we will explore the final seconds of the motion, the physics of the stop, and the hidden danger of the 2026 high-voltage safety systems when the chassis is twisted like a pretzel. Marcus is no longer moving, but the clock is ticking faster than ever. The kinetic energy that once propelled Marcus's 2-ton sedan has finally been exhausted, converted into heat through friction, and into the mechanical work of crushing steel and shattering glass. But the cessation of movement does not mean the physics of the event have concluded. In fact, for Marcus, a new and quieter set of physical laws is now in effect. The car is at a total standstill, resting on its mangled roof in a ditch on the side of a Pennsylvania highway in 2026. As the dust settles and the smell of ozone from the deployed airbags fills the cabin, Marcus is experiencing the post-roll state. He is suspended upside down, held in place only by the 3-point seatbelt that has transitioned from a safety restraint into a high-tension suspension cable. At this moment, gravity, which was Marcus's enemy during the tumble, becomes a constant, oppressive force. Marcus weighs 180 pounds. In a normal seated position, that weight is distributed across the large surface area of the seat cushion and the skeletal structure of his pelvis. Now, that entire 180 pounds is being funneled into the 2-inch wide polyester webbing of the seatbelt. This creates a massive amount of pressure, calculated as force divided by area, across his collarbone and pelvic region. If we look at the physics of the buckle itself, we see the first major obstacle of the post-roll environment. The release mechanism of a 2026 seatbelt is a precision-engineered latch designed to withstand thousands of pounds of force during an impact. However, it is not designed to be easily released while under a constant 180-pound static load. To press the red button and release the latch, Marcus would need to provide enough counterforce to lift his own body toward the floor of the car, relieving the tension on the internal spring-loaded cam. For a disoriented, potentially injured person, this simple mechanical requirement can be an insurmountable physical challenge. While Marcus is hanging there, his internal biology is struggling with the physics of inversion. The human circulatory system is optimized for an upright or prone position. It utilizes a series of one-way valves and the constant assistance of gravity to return blood from the lower extremities to the heart. When Marcus is inverted, this entire system is flipped. This leads to a cephalad shift, a massive movement of fluid toward the head. In this 2026 deep dive, we have to look at the hydrostatic pressure within the vascular system. The blood pressure in Marcus's brain increases significantly because the heart is now pumping down toward the head, while gravity is no longer helping the blood drain back toward the torso. Historical trends in inversion trauma suggest that prolonged time in this position can lead to a dangerous increase in intracranial pressure and a decrease in the efficiency of the respiratory system. Because Marcus's weight is pulling him into the seatbelt, the shoulder strap is likely compressing his chest, making it harder for his diaphragm to expand against the weight of his own internal organs, which have now shifted toward his head. Simultaneously, the 2026 electric vehicle under Marcus is performing its own set of high-stakes physical calculations. Marcus's sedan is powered by an 800-volt battery architecture. In a rollover where the chassis has been twisted into a pretzel-like shape, the risk of a high-voltage short circuit is a primary concern for automotive engineers. This is where the physics of the pyrotechnic fuse, or pyro switch, comes into play. The moment the rollover sensors detected an inversion greater than 90 degrees, a small controlled explosion occurred within the battery's junction box. This physical disconnection happens in less than 30 milliseconds, effectively isolating the high-voltage energy within the armored battery pack and preventing the car's metal frame from becoming energized. Without this pyro switch, the mangled metal pillars of the car could potentially carry a lethal current, turning the vehicle into a giant capacitor. However, even with the high-voltage system isolated, there is the matter of elastic potential energy. When the car's frame was crushed during the multiple revolutions, the steel pillars were bent beyond their elastic limit and into the realm of plastic deformation. But they did not lose all their tension. The car's body is now like a tightly wound spring that has been partially released, but is still holding significant internal stress. This is why doors in a rolled vehicle are often impossible to open by hand. The door frame has been squeezed by the shifting weight of the car, creating immense frictional force between the latch and the striker. Case studies in accident reconstruction show that it can take several tons of hydraulic force to overcome the friction created by a deformed roof pillar pressing down on a door frame. Marcus is not just trapped by gravity. He is trapped by the residual energy stored in the very metal meant to protect him. Furthermore, we must consider the environmental physics of the 2026 cabin. Modern vehicles are designed with incredible seals for noise reduction and climate control. When a car is upside down in a ditch, these seals, combined with the deployment of multiple airbags, can create a claustrophobic environment with limited airflow. The airbag propellant, typically nitrogen gas filtered through a cornstarch or talcum powder lubricant, creates a thick dust that can irritate the lungs. In a multi-revolution roll, the structural integrity of the fuel lines in a gas car, or the cooling lines in an EV like Marcus's, may have been compromised. Marcus might be smelling the sweet, chemical scent of glycol-based coolant, or the pungent aroma of hydraulic brake fluid. If these fluids leak onto the hot surfaces of the electric motors or the friction-heated brake rotors, the potential outcomes include the transition from a mechanical accident to a chemical or thermal event. The physics of the stop is also about the ground beneath the car. Because Marcus's car is an EV, it has a very high mass-to-volume ratio. This means that when it finally stopped, it likely dug deep into the Pennsylvania soil. If the car is resting in a soft embankment, the weight of the vehicle can cause it to continue to settle over several minutes. This settling can further compress the roof or shift the center of gravity, potentially leading to a secondary roll if the car is perched on an unstable slope. Rescue teams in 2026 use specialized physics-based stabilization tools, struts and jacks, to arrest this potential energy before they even attempt to reach Marcus. Marcus is currently caught in a state of static equilibrium, but it is a fragile one. Every breath he takes is a struggle against the physics of his own weight and the tension of the polyester webbing. The clock is ticking because of the physiological toll of the inversion. His body is fighting a losing battle against the hydrostatic pressure in his brain, While the car's structure is under a constant load, it was never meant to sustain for long periods. But what happens when the first responder arrives? What are the specific physics of the extrication process? How do they cut through boron steel without collapsing the remaining survival space? And what happens to Marcus's blood pressure the moment he is finally turned right side up? In the next part, we will explore the rescue physics, the high-pressure world of hydraulic shears, the science of patient stabilization during a flip, and the sudden dangerous physiological shift known as reflow syndrome that occurs when an inverted victim is finally leveled. The motion has stopped, but the most critical phase of survival is just beginning. The arrival of first responders on the scene of Marcus's 2026 rollover marks the transition from uncontrolled kinetic chaos to highly calculated mechanical intervention. When a paramedic or a heavy rescue squad pulls up to that ditch in Pennsylvania, they do not simply run to the vehicle and yank on the door handle. To do so would be to ignore the precarious physics of a car resting on its roof. The vehicle is currently in a state of unstable equilibrium. Because the roof of Marcus's sedan is curved and partially crushed, the entire 6,000-pound mass is balancing on a narrow, shifting fulcrum. Any change in the distribution of weight, such as a responder leaning against the chassis or Marcus shifting his position inside, could trigger a secondary roll. The first step is the physics of stabilization. Responders utilize specialized equipment known as stabilization struts. These are adjustable heavy-duty poles that create a wider footprint for the inverted vehicle. By placing these struts at calculated angles against the frame and tensioning them with ratcheting straps, the responders are essentially creating a temporary tripod out of the car. This moves the center of gravity into a much larger base of support, arresting the potential energy that is still stored in the vehicle's position on the embankment. Historical trends in technical rescue show that without this stabilization, the vibration of hydraulic tools alone can be enough to cause a car to slide further down a slope, potentially crushing both the victim and the rescuers. Once the car is a rigid, non-moving object, the focus shifts to the physics of the cut. As we established, Marcus's 2026 sedan is constructed with ultra-high-strength boron steel in the pillars to protect the survival space. This material is designed to resist deformation, which also means it resists cutting. Standard reciprocating saws that would have sliced through a 1990s-era car would simply dull their blades against this 2026 alloy. Instead, the rescue team uses hydraulic cutters, often colloquially called the jaws of life. These tools operate on Pascal's principle. A change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. The rescue tools pump generates upwards of 10,000 pounds per square inch of hydraulic pressure. This pressure is funneled into a piston that drives the massive hardened steel blades together, with a crushing force of over 200,000 pounds. When these blades meet the boron steel A-pillar of Marcus's car, the physics is a battle of material yield strengths. The cutter must exceed the ultimate tensile strength of the pillar to initiate a fracture. In 2026, this process is monitored by integrated sensors in the tools that adjust the cutting angle to prevent tool twist, a dangerous phenomenon where the resistance of the high-strength steel causes the entire hydraulic tool to violently rotate in the rescuer's hands. As the pillars are severed, the responders are carefully managing the relief of tension. Remember, the car's frame is currently under immense internal stress from the crash. As a pillar is cut, that stored elastic potential energy can be released suddenly, causing the metal to snap or shift by several inches. To prevent this, rescuers use step chalking, inserting wooden or composite blocks into the gaps as they are created to maintain the structural gap and prevent the roof from further encroaching on Marcus's head. Now imagine the perspective from inside the cabin. Marcus is still hanging upside down. The rescuers have managed to create an opening, but they face a critical biological physics problem: the seatbelt let down. Marcus is a 180-pound mass suspended 4 inches above the crushed headliner. If a rescuer simply reaches in and depresses the seatbelt release button, Marcus will fall. Because his neck and spine have already been subjected to the extreme G-forces of the roll, a 4-inch vertical drop onto his head could be the final load that causes a catastrophic spinal cord injury. To solve this, they use a soft letdown technique. 1 or 2 rescuers enter the survival space and use their own bodies or specialized inflatable bags to support Marcus's weight from below. Only when his torso is fully supported do they cut the seatbelt webbing. This transition from being suspended to being supported is the first time in several minutes that the 180 pounds of pressure has been removed from his chest and collarbone. While this is a relief for his breathing, it triggers the beginning of a dangerous physiological transition. As Marcus is leveled and prepared for extraction, his body undergoes a massive hydrostatic reset. For the duration of the inversion, gravity was pulling his blood toward his brain and his internal organs toward his diaphragm. The moment he is moved into a horizontal right-side-up position, that gravity vector flips 180 degrees. This causes a sudden pooling of blood in his lower extremities. His heart, which has been working against gravity to pump blood up to his legs while he was inverted, suddenly finds itself pumping into a low-pressure void. This can lead to a rapid drop in blood pressure, known as orthostatic hypotension, which can cause Marcus to lose consciousness, even if he was previously awake and talking. But there is a deeper chemical physics at play called reflow syndrome, also known as reperfusion injury. While Marcus was trapped, the pressure of the seatbelt or the compression of his limbs against the mangled interior may have restricted blood flow to certain muscle groups. In these ischemic zones, the cells began to switch to anaerobic metabolism, creating a buildup of metabolic waste products like lactic acid and potassium. If a limb was severely compressed, the muscle cells may have even begun to break down, releasing a protein called myoglobin. The moment Marcus is leveled and the pressure is removed, the circulatory dam breaks. This acidic, potassium-rich and myoglobin-heavy blood rushes from his extremities back to his heart and lungs. This is a chemical surge that the body is not prepared for. High levels of potassium can interfere with the electrical conductivity of the heart, leading to potential outcomes like cardiac arrhythmia. Myoglobin, meanwhile, is a large molecule that can act like sludge in the microscopic filters of the kidneys, leading to acute renal failure. Historical trends in crush medicine show that victims who appear stable and alert while trapped can suddenly deteriorate minutes after being freed due to this sudden chemical reflow. In 2026, Marcus's medical team is likely using real-time bioliquid analysis drones or handheld sensors to monitor his blood chemistry during the extraction itself. They may administer intravenous fluids or specific medications to buffer the acidity of the blood before they even move him to the stretcher. This is the golden hour of trauma physics, the 60-minute window where medical intervention can most effectively counter the physical and chemical damage of the crash. Marcus is now out of the car. He is on a spine board, his head immobilized, and his vitals are being stabilized by a team of professionals. The twisted metal of the 2026 sedan remains in the ditch, a silent monument to the incredible forces it just withstood. But the story of the rollover doesn't end at the hospital. To prevent the next Marcus from entering that ditch, we have to look at the post-crash forensic physics. How do engineers look at the scratch patterns on the roof to determine the exact speed of the roll? What do the black box data logs from 2026 vehicles tell us about the final milliseconds before the trip? And most importantly, how is the data from this specific crash being used to design the unflippable cars of the future? In the next part, we will dive into the world of accident reconstruction, looking at the laser scanning of crash sites and the math behind the slide-to-stop calculations. We are moving from the rescue to the investigation. The investigation begins the moment the ambulance sirens fade into the distance. Imagine a forensic engineer named Alex arriving at the Pennsylvania ditch in late 2026. The scene is a chaotic tapestry of debris, fluid spills, and deep gouges in the earth. But to Alex, this is a data-rich environment that can be solved with the precision of a mathematical proof. In 2026, the primary tool for this task is no longer a simple tape measure and a camera. It is a high-definition terrestrial LiDAR scanner. This device, mounted on a tripod at the center of the crash site, pulses millions of laser beams per second in a 360-degree arc. Each pulse reflects off the mangled car, the scorched asphalt, and the disturbed soil, returning to the sensor to create a point cloud. This is a three-dimensional digital twin of the accident scene, accurate to within a single millimeter. Alex uses this digital twin to perform a forensic deep dive into the kinematics of the crash. The first thing he looks for are the tire marks. On the asphalt leading up to the ditch, there are distinctive, curved marks known as yaw marks. These are not skid marks from braking. They are scuff marks created when a tire is still rotating, but is being forced to slide sideways because the vehicle's lateral momentum has exceeded the tire's available grip. By measuring the radius of these curves within the point cloud, Alex can apply the critical speed formula. This formula V equals GIR, where g is gravity, r is the radius of the curve, and mu is the coefficient of friction, allows him to determine exactly how fast the car was traveling the moment it began to lose control. In 2026, coefficients of friction are more complex to calculate because modern road surfaces often incorporate high-friction polymers designed to reduce hydroplaning, meaning Alex must cross-reference the local Department of Transportation data for this specific stretch of highway. Once the speed of the yaw is established, Alex moves his focus to the trip point. He identifies a deep furrow in the soft soil at the edge of the embankment where the wheel rims bit into the earth. This is the fulcrum we discussed earlier. By analyzing the depth and angle of these gouges, Alex can calculate the impulse force that initiated the rotation. He looks for the first point of roof contact, which is evidenced by a distinct impact crater in the dirt and paint transfer on the rocks. This paint transfer is a physical fingerprint. By matching the height of the paint on the rock to the corresponding damage on the vehicle's roof pillars, he can determine the pitch and roll angle of the car at the exact millisecond of the first impact. However, the physical evidence on the ground is only half the story in 2026. Alex now turns to the vehicle's event data recorder, or EDR, often called the black box. In 2026, these devices are far more advanced than the simple loop recorders of the past. They are integrated into the vehicle's central AI processing unit. Alex connects his diagnostic tool to the car's surviving data port, or if the port is destroyed, he extracts the hardened memory chip directly from the wreckage. The EDR provides a high-fidelity telemetry log of the 5 seconds leading up to the trip. It records the steering wheel angle, the throttle position, the individual brake pressure at each wheel, and the yaw rate. This data allows Alex to see exactly what the driver, let us call him Jordan from our earlier scenario, was doing. Did Jordan tap the brakes, causing a forward weight transfer that made the rear tires lose grip? Or did the electronic stability control attempt to intervene and fail because the lateral G-forces were simply too high? In 2026, cars also record data from their external environment sensors. Alex can see the point of view of the car's cameras and LiDAR as it approached the ditch. This provides a case study in human-machine interaction. He might find that an object in the road, which Jordan swerved to avoid, was actually a piece of light debris that wouldn't have caused a crash, but the human instinct to swerve created the high-side trip that flipped the vehicle. Next, Alex performs a scratch pattern analysis on the exterior of the car. This is a specialized field of forensic physics that looks at the directionality of the striations on the metal. If the scratches on the roof are parallel to the longitudinal axis of the car, it indicates a pure barrel roll. If they are diagonal, it confirms that the car was yawing or spinning like a top while it was rolling. The length of the slide-to-stop marks on the roof is particularly telling. Using the formula V equals V meets D, where D is the distance the car slid on its roof, Alex can determine the velocity of the car at the moment it completed its final revolution and began its final slide. The friction coefficient mu for a crushed steel roof on asphalt is typically around 0.4 to 0.5, but in 2026, the use of composite roof materials and specialized safety coatings means Alex has to account for variable friction rates. Another critical piece of evidence is the fluid spray pattern. When the car was rotating at 120 revolutions per minute, any fluids that leaked, coolant, brake fluid, or battery dielectric oil, were subject to massive centrifugal forces. These fluids are flung outward in a tangential path. By mapping the location of fluid droplets on the road and the surrounding trees, Alex can work backward to determine the exact position of the car in three-dimensional space at the moment the fluid lines ruptured. This is essentially a specialized form of bloodstain pattern analysis applied to automotive engineering. It tells him at what point in the roll the chassis experienced the most extreme structural flex. Historical trends show that this forensic data is vital for more than just insurance claims or legal proceedings. In 2026, every catastrophic rollover in the United States is fed into a national database used by safety engineers. Alex's findings will be uploaded into a massive simulation engine that runs thousands of what-if scenarios. What if the car's center of gravity had been 1 inch lower? What if the tires had a slightly lower sidewall stiffness? This iterative physics modeling is how the industry moves toward potential outcomes where rollovers are no longer fatal. Alex is also looking for phantom failures, microfractures in the suspension that may have occurred before the trip. Using ultrasonic testing on the surviving components, he can determine if a ball joint or a tie rod failed under the stress of the initial swerve, which would have made the rollover inevitable regardless of the driver's skill. This is the deep dive into the why behind the physics. It is the bridge between a tragedy in a Pennsylvania ditch and the future of automotive safety. We have now covered the trip, the tumble, the biological impact, the rescue, and the forensic investigation. We have seen how 2026 technology tracks every joule of energy from the moment of distraction to the final slide. But there is one final piece of the puzzle. How do we take everything we have learned from this forensic analysis and use it to build a vehicle that actively fights the laws of physics? Is it possible to create a car that refuses to flip, even when a trip is imminent? In the final part of our masterclass, we are going to look at the future of active aero, counter-moment braking, and the radical 2027 safety concepts that are designed to make the car upside-down scenario a relic of history. The investigation is over. Now it is time for the solution. The transition from investigating the wreckage to engineering the solution represents the ultimate challenge in automotive physics. Imagine a driver named Emily in late 2026, operating a prototype vehicle that integrates the next generation of safety systems. As we have seen in previous sections, the primary enemy in a rollover is the combination of a high center of gravity and uncontrolled lateral momentum. To combat this, engineers are moving beyond passive structures like boron steel pillars and entering the realm of active physical intervention. This begins with the concept of active aerodynamics. In high-performance racing, wings and spoilers are used to create downforce, pushing the tires harder into the track. In Emily's 2026 prototype, this principle is repurposed for stability. When the vehicle's onboard inertial measurement unit detects a lateral tilt exceeding a specific threshold, say 12 degrees within 50 milliseconds, actuators in the rear spoiler and front splitters adjust their angle of attack. By creating an asymmetrical aerodynamic load, the car can generate hundreds of pounds of downward force specifically on the wheels that are attempting to lift. This is the physics of utilizing the air itself to rewrite the static stability factor in real time. The second pillar of this solution is the evolution of torque vectoring and counter-moment braking. While traditional electronic stability control or ESC was a reactive system that applied brakes to prevent a skid, 2027 concept vehicles utilize the independent nature of electric motors to create active stabilization. In Emily's vehicle, each of the four wheels is powered by its own dedicated motor. If the car enters a violent swerve and the sensors detect the beginning of a trip, the computer does not just brake the outside wheels. It performs a high-frequency calculation of the longitudinal and lateral force coupling. It can instantly apply a burst of positive torque to the wheels on the side that is lifting while applying negative torque regenerative braking to the wheels on the side that is planted. This creates a rotational counter-moment that effectively tries to twist the car back toward a level plane. Historical trends suggest that this level of granular control can prevent an untripped rollover at speeds 20% higher than standard systems. However, the most radical shift in the physics of prevention lies in predictive active suspension. As Emily approaches a potential hazard, her vehicle is not just reacting to the road, it is reading it. Using a combination of short-range LiDAR and high-frequency ultrasound, the car scans the surface ahead for curbs, deep ruts, or soft soil, the very things that cause the soil trips we analyzed in Sarah's case study. When a tripping hazard is identified, the active suspension system, which operates on high-voltage electromagnetic actuators rather than traditional slow-moving hydraulics, can adjust the ride height in less than 20 milliseconds. If Emily is forced into a sharp left turn, the suspension on the right side of the car, the side that would normally compress and allow the body to lean, instantly stiffens and extends. Simultaneously, the left side drops. This effectively counters the body roll and keeps the center of gravity as low and as centered as possible. It is the physical equivalent of a person widening their stance and lowering their hips before being pushed from the side. We must also look at the role of vehicle-to-everything or V2X communication as a tool of physics. In the United States in 2026, highway infrastructure is increasingly integrated with vehicle AI. The panic swerve is often the result of a human driver's inability to perceive a hazard until it is too late. In Emily's case, if there is a stalled vehicle or debris 200 yards ahead around a blind curve, the road sensors transmit that data to her car. The vehicle's AI can then initiate a stability-optimized deceleration. Instead of a jagged high-G steering input that risks a rollover, the car calculates a smooth, mathematically optimized path that keeps the lateral acceleration well below the 0.8 G threshold. By removing the erratic nature of human reaction times and replacing it with the precision of kinematic modeling, the trip is prevented before the driver even perceives the danger. But what if the laws of physics are simply too overwhelming? What if a vehicle is struck by another heavy object and forced into a roll regardless of its internal systems? This is where the 2027 external safety shell concepts come into play. Researchers are currently developing case studies on external deployment airbags. These are high-volume, high-pressure bags located behind the body panels along the roof rail and the door sills. If an inevitable rollover is detected, these bags deploy outward before the car even touches the ground. This changes the physics of the impact from a metal-on-ground event to a damped oscillation event. The airbags increase the deceleration distance by several inches. In physics, if you increase the distance over which work is done to stop an object, you decrease the force. By turning a hard impact into a soft, managed landing, the peak G-loads on the occupant's spines can be reduced by over 50%, potentially shifting the outcome from a catastrophic injury to a survivable event. Furthermore, we are seeing the introduction of the untrippable wheel and tire assembly. These designs incorporate a flexible, non-pneumatic tire structure that can deform laterally without debeating from the rim. In our deep dive into the soil trip, we saw how the metal rim biting into the earth acted as a lethal anchor. These 2027 tires are designed to fold under extreme lateral pressure, allowing the wheel to slide across a curb or through soft dirt rather than digging in. This converts the rotational energy back into sliding kinetic energy, which can then be dissipated through the vehicle's standard stability systems. It is a fundamental redesign of the interface between the machine and the earth. Inside the cabin, the final part of the solution is the dynamic survival cell. In 2026, we are seeing seats that are no longer bolted rigidly to the floor. Instead, they are mounted on a multi-axis gimbal system. If the car begins to roll, the seat itself rotates internally to keep the occupant as level as possible, or at the very least, to ensure that the impact forces are always distributed through the strongest parts of the human skeletal system, the pelvis and the shoulders, rather than the fragile cervical spine. This is the ultimate application of biomechanical physics, treating the human body as a precious cargo that must be isolated from the violent rotation of the outer shell. As we conclude this masterclass, it is clear that surviving a car going upside down is not about luck. It is about the mastery of forces. We have deconstructed the static stability factor, analyzed the violent mechanics of the soil trip, explored the structural limits of boron steel, and looked into the chemical and biological trauma of inversion. The cars of 2026 and 2027 are being built as physical fortresses, designed to fight Newton's laws at every turn. But even with all this technology, the most powerful tool remains understanding. Knowledge of the point of no return, and the mechanics of weight transfer is what allows an engineer to build a better car and a driver to make better decisions. The physics of the flip are uncompromising, but they are also predictable. Every gouge in the dirt and every bent pillar tells a story of energy looking for a way out. By capturing that energy and redirecting it through active aero, torque vectoring, and predictive suspension, we are entering an era where the car upside-down scenario becomes an engineering anomaly rather than a common tragedy. The investigation into these forces never truly ends. It only evolves. The data from every 2026 crash is a stepping stone to a 2027 solution. While we have mastered the physics of the rollover on dry, predictable surfaces, a new and even more complex set of variables arises when we introduce the unpredictable nature of extreme weather and environmental degradation. What happens when these same high-G forces are applied to a vehicle on black ice, or during a hydroplaning event where the coefficient of friction drops to near zero? Does the active aero still work when the air is thick with snow? In our next deep dive, we will explore the physics of the zero-friction environment, looking at how AI handles the total loss of control and the radical new tech designed to find grip where none exists. The journey into the science of survival continues.